So first given polynomial generator is x power of 6 plus 1, right? Here degree of polynomial is 6, r is equal to 6. Just apply the statement that we discussed. All burst errors with L is lesser than or equal to 6 will be detected, and L is equal to 6 plus 1, that is sum, with the probability 1 minus 1 divided by 2 whole power of 6 minus 1 is equal to 0.9687. And third one is all burst error with L is greater than 6 plus 1, that is 7, right? Will also be detected, and the probability is 1 minus 1 divided by 2 whole power of 6, and simplify this. Similarly, you can calculate for the given generator, that is x power of 18 plus x power of 7 plus x plus 1. Okay, here the degree of polynomial is 18, right? So that is r is equal to 18. Again, apply same statement and substitute the value in the place of r and find the probability as well. Okay, and the next given polynomial generator is x power of 32 plus x power of 23 plus x power of 7 plus 1. And here you can see degree of polynomial is 32. Okay, again apply the statements here. Find out L, which is lesser than or equal to 32, which are equal to 32 plus 1 or greater than 32 plus 1, and find the probability for the same. Okay, so this is how you can find out whether the given generator polynomial will detect error that are present in the data. Okay, so next we'll move on to the next topic, that is checksum. So okay, before that, a few standard CRC polynomials used, that is polynomial generator used, okay, for the CRC. Okay, so that is CRC 8, which is x power of 8 plus x power of 2 plus x plus 1. So this polynomial is used in ATM header. Okay, so and CRC ATM is asynchronous transfer mode header. Okay, so that this particular polynomial is used. CRC 10 is used in ATM AAL, that is ATM adaptation layer protocol. Okay, and next CRC 16, that is x power of 16 plus x power of 12 plus x power of 5 plus 1. It is used in HDLC, that is high level data link control. Okay, and the last one is CRC 32, where this polynomial is used in LAN, that is local area networks. Okay, these are the few CRC polynomial used. Next topic is checksum. See, checksum, once yeah, checksum, it is error detecting technique which is used or which can be applied on the message of any length. Okay, so again checksum is another type of error detecting technique. Okay, and it is used at the network and transmission layer rather than what we discussed CRC and a data link layer. Okay, checksum, it is an error detecting technique. Okay, and it is used at the network layer and the transport layer of TCP/IP network model. Okay, now we'll see how actually this checksum can be applied to detect errors in the message. Okay, first thing is what the given message. Okay, this is the message is first you have to divide into embeds. You can see here the given message which you want to communicate with the another end user, that is receiver, is divided into embeds units. Okay, now there is a generator here, you can see here, right? So this generator takes this as input and generates extra embed. Okay, and this is called as checksum. So this is called as checksum. Okay, the given message is divided into mbit units. Okay, and this is given as input for the generator. This generator generates mbit, that is extra m bits, that we call it as checksum. Okay. Now this message, this m bits units are there, no? This message and the checksum together is transmitted over the transmission link. Okay. Once this message plus checksum received at the receiver end, it is given to the checker. Okay. With this the given as input for this checker. Okay. This checker creates a new checksum from the combination of message plus checksum here. Okay. So if this new checksum is all zeros, okay, then message will be accepted. I'll repeat. For this checker, this message plus checksum is given as input. Then this checker generates new checksum. Okay. And if these, what are the bits that are present in the new checksum, must be all zeros. Okay. Then the message will be delivered, extracted at the receiver end. Okay. If any one bit is 1, then that particular message will be discarded. Okay. This is how checksum works. So here the message will be divided into m bit units. Okay. And that is fed as input for the generator. This generator generates extra m bit, that we call it as checksum. This checksum along with the m bits unit is transmitted over the transmission link and delivers at the receiver end. Now it's the duty at the receiver end that the received message need to be checked whether it is corrupted or not, right? So for that, the received message plus checksum is given as input for the checker. Okay. This checker generates new checksum which may have m bits, and this all m bits must be 0. Then only the received message is treated as a valid message. Okay. Or else this will be discarded. Okay. Let's see an example under this checksum. Okay. Suppose the message is list of 5 4-bit numbers. That means you want to send 5 numbers to the receiver. Okay. And each number will be represented with the help of 4-bit. See, if I need to send a number 0, then I'll represent 0 as in the form of 4 bits. That is 0, 0, 0, 0. Okay. So that in that way. So that we want to send it to a destination. Okay. Now, in addition to sending these numbers, okay. So first what we will do, we send the sum of the numbers. Say along with, consider these are the 5 numbers that I want to send it to receiver. That is 5 numbers: 7, 11, 12, 0, 6. Okay. Now I will send these numbers along with the sum of these numbers. What is its sum? 7 plus 11 plus 12 plus 0 plus 6. It is 36. So now I will send 7, 11, 12, 0, 6, 36. Okay. So this will be sent to the receiver. Okay. Then what receiver will do? Once the receiver receives the data, he adds the 5 numbers and compares the result with the sum. So what he'll do? He'll add all the 5 numbers received and again he'll add it up and then he'll compare with the sum that is sent in the message. Okay. If the 2 numbers are same, then the receiver assumes no error, accepts the 5 numbers and discards the sum. Okay. This is how it works. Now I said 7. Here you can see here 7, 11, 12 and 0 as well as 6. Okay. All these numbers can be represented with the help of 4 bits. You all know, right, how to write a binary number for a decimal number, right? So I'll just show you the table here. Okay. If you want to send 0, then you will convert it into 4 bits. That is 0, 0, 0, 0. So in this case, 7, 11, 12, 6, 0, 6, right? So 7, 12, 1406. So all can be represented in the form of 4 bits and can be sent to the receiver. Now the question is sum. Sum is 36 here. You can't represent 36 in the form of 4 bits because 4 bits you can use it till only number 15, right? So here for 15 it is 1111. If you want to represent 16, then again you have to convert that into binary form. That will not be in the form of 4 bits, right? So here, yeah, here 36, I've converted it into binary form. See here, it is 6 bits. That is 100100. So this is not 4 bit, right? It is 6 bit, right? So one solution for that to represent such, if you end up with the sum which is greater than 15, okay, then a solution for that problem is using one's complement arithmetic. I'll repeat, problem to solve. If you need to represent a number, if you can't represent that particular number in the form of 4 bits, then solution for that is one's complement arithmetic. Okay, so that is, here we can represent numbers between 0 to 2 power of m minus 1 using only m bits. Okay, so if the number has more than m bits, okay, if the number has more than m bits, the extra leftmost bits need to be added to the m rightmost bits. Adding this extra leftmost bits to the m rightmost bits is called as wrapping. I'll just tell you. Let me see here. This 36 is represented with the help of 6 bits, right? Now, wrapping is one that the leftmost 2 bits here, 1, 2, 3, 4. You just leave 4 bits here. Take last 2 bits. Okay, that is 1, 0. You consider 1, 1, 0 here and add this 1, 0 to rightmost bits. That is 1, 0. Or you can see here. Okay, this is leftmost bit need to be added to the rightmost bit. Okay, now you have to perform addition operation on this. So now you can convert this number into 4 bits only, right? 0, 0, 0, 0, 1, 1 and 0, 1. So you can write this as 0, 1, 1, 0. Okay, so 36 will be represented as 4 bits only, that is 0, 1, 1, 0 with the help of one's complement arithmetic. Okay, I hope this is clear to everyone. So that is what I explained here. And that adding leftmost bits to the m rightmost bits is called as wrapping. Okay, yeah, next. So let's solve a problem now. Okay, as per the checksum, I want to send the 5 numbers here, 7, 11, 12, 0, 6. Okay, so as per the checksum, I need to include checksum also, right? So for along with 5 numbers, I'll take checksum as 0 here and I'll add it up. Okay, 7 plus 11 plus 12 plus 0 plus 6 plus 0 is 36. Okay, see here, this is checksum, pink, whatever I have written in the pink color. Okay, this is checksum. This is checksum. So you need to add all these number including checksum. That comes to 36. Okay, now you know that 36 can't be represented in the form of 4 bits. See, because here the method followed here, whatever number that you send, that should be converted into 4 bits, right? But you can't represent 36 in the form of 4 bits. That's why you need to perform wrapping. You need to perform wrapping. That is 36 in the binary form. I mean 36, if you convert that into binary form, it will be 100100. Okay, binary representation of decimal number 36. Now you have to perform wrapping, that is the leftmost bits, that is 1 and 0. These two are the leftmost bits. I'm taking this and adding to the rightmost bits, that is 1 0. Add it up, 0 0 0 0 1 1 1 0. Okay, for this you have to take complement. So once, how do you take one's complement? Just okay, I'm sorry students, I had network issue. Okay, let's continue. So this 36 you have to convert it into 4 bits, right? So I'm adding leftmost bits to the rightmost bits. So add it up, you will get 0 1 1 0. So which is nothing but 6 here. Now you have to complement it. Okay. So next step is complement. You have to complement after wrapping. So convert 0 to 1, 1 to 0, 1 to 0, 0 to 1. Okay. Now the finally the bits are 1, 0, 0, 1. Okay, so if you convert this binary to decimal, then decimal number for this binary is 9. Okay, so now I will be sending this 5 numbers and the checksum. Okay, that is 9. 36 is after wrapping, sum will be 6, and again you have to convert it, you have to complement this, then you will get 9. So I will be sending 5 numbers 7, 11, 12, 0, 6 and the checksum. Okay, so you can see here. Along with the data, checksum is also sent. Once it is received at the receiver end, what happens? The receiver will add up all the numbers received in the packet. That will come to 45. Right? Now 45, again you can't represent this number in the form of 4 bits. Right? Again, convert this 45 into binary form. Consider the last 2 bits, leftmost bits, add it to the rightmost bits. Okay, then add up 101, 011, 11. Okay, for this you complement it. When you complement this, what happens? 1 will change to 0, 1 to 0, 1 to 0 and 1 to 0. So you will end up with value as 0 0 0 0, right? So that means 0. So if you get a value at the last as 0 0 0 0, then it confirms that the data which is received at the receiver end is the proper one. It is not corrupted. Okay, that is how the checksum is what it works in this way. Okay, the message along with the checksum, you have to send it over the transmission link. Once it is received at the receiver end, again here receiver has to check the final answer. Is it 0 0, right? Okay, if whatever the new checksum is calculated at the receiver end should be 0. Okay, or else the received data will be discarded. Fine, that is how it works. Next one internet checksum is given, which is used in the internet network. Okay, internet checksum, where at the sender side, first the message is divided into 16-bit words. Okay, so then what happens? The checksum value is added, that is 0. Okay, first message is divided into 16-bit words and the value of checksum word is set to 0. Third step is that all words including the checksum are added using ones complement addition. This is the third step. Fourth step, the sum, whatever this after performing addition here, the sum is complemented and then it becomes the checksum. Okay, and this checksum is sent through the transmission link along with the data. Okay, these are the 5 things that happens at the sender side. Now, what are the steps taken at the receiver side? The message, that is including checksum, again it is divided into 16-bit words. All words are added using ones complement addition and the sum is complemented. Okay, here after performing addition, the sum is complemented and becomes the new checksum. If the value of new checksum is 0, message is accepted, otherwise it will be rejected. Okay, let's see an example here. Say, as I said, it is 16-bit word. That means the data will be represented in the form of hexadecimal. Okay, in the previous example, it was in the form of binary. Okay, so 4 bits. Here it is 6 bits. So hexadecimal value will be considered. Okay, so here the given data is divided into 16-bit words. Okay, you can see all the values are written in hexadecimal. Now consider, okay, this is the message that sender wants to send it to receiver. This 4 row values. Okay, 4 cross 4. Okay, this is the data that sender wants to send it. Okay, now for this I'm adding checksum. What is checksum? It is 0, as I explained in the previous slide at the sender side. Okay. Now perform addition between these values. That is f plus 7 plus a plus e plus 0. So how much? So you can see here f means 15. Sorry, f means 15. Okay, f here it is 15. Okay, I have taken in the binary form. Okay, okay. Sorry. I would have taken hexa with the decimal one, right? So here 9, okay, A means 10, right? This is 10, right? And B in the sense it is 11, C it is 12, right? And D it is 13, and E it is 14, and F it is 15. Okay, so here you have to add all the values, that is 15 plus 7 plus 10 plus 14 plus 0. Okay, that may comes to 46. Okay, now you convert 46 to hexadecimal. Okay, if you convert 46 to hexadecimal, the answer will be 2e. Okay, so here you can see e is written here, 2 is considered as carry. Okay, so in the same way you add up this value. Okay, and answer comes to b 1b. B is written here, 1 considered as carry. Again add all these value, then you will get it as 0f. Okay, so that is 0 is carry here, and f is the answer here. Again add up all the values here, that comes to 18, where 8 is written here, and 1 is considered as carry. So this one so the after performing addition operation here, the final answer is 8FBE. Okay, so whatever one carry is there, that is added to the rightmost value. Okay, E plus 1, that becomes F. Right, see, all the values should be in the form of hexadecimal only, 16-bit. Okay, so E plus 1 is F, B, F, 8. Okay, this is the sum. Okay, for this sum you have to find the complement. How do you find the complement? Yes, you just check with FFF. Okay, F, subtract it, FFF. Okay, so if you subtract 8FBF from FFF, you will get answer as 7040. Okay, this is the checksum that is generated at the sender side. Okay, now as per the details that I've discussed in the previous slide, this whole data as well as checksum will be sent over the transmission link, right? So once it is received at the receiver end, what happens here? The data, that is this whole thing, data along with the checksum is considered. Okay, perform addition operation here. Okay, addition operation with respect to all the numbers, with respect to all the columns here, and whatever one carry is there, that should be added to this rightmost value. Okay, so when you add it up, it will comes to FFFF. Now takes complement here. Then once you take the complement, obviously, I mean, if you subtract FFFF from FFFF, obviously the generated new checksum is 0, right? 15 minus 15 is 0. Again 15 minus 15 is 0, right? So the newly generated checksum is 0. So now you can conclude that the received data at the receiver end is the proper one, and it is not corrupted. Okay, that is how internet checksum is calculated with respect to this example. Okay.